What if the future of technology hinges on materials just a single atom thick? A groundbreaking study from the University of Pennsylvania is shedding light on how to create these ultra-thin 2D materials, which could revolutionize everything from smartphones to medical devices and renewable energy systems. This research isn't just about building better gadgets. It's about unlocking a new era of innovation by mastering the science behind these atomic-scale wonders. But here's where it gets controversial. While the potential is staggering, the path to practical applications is fraught with challenges that even experts can't agree on. Let's dive into the details and explore why this work is both exciting and contentious. The Penn team's work focuses on the chemistry and geometry of 2D materials. Think of them as super thin layers of atoms, so delicate they're measured in nanometers. These materials, like graphene or transition metal dichalcogenides, have unique properties. They're incredibly strong, lightweight, and conduct electricity and heat with near-perfect efficiency. But creating them consistently and at scale has been a puzzle. The team's breakthrough lies in understanding how to control the structure of these materials during synthesis. For example, by tweaking chemical reactions and adjusting the way atoms bond, they've found ways to produce materials with specific properties tailored for different uses. This is like being a molecular architect. You don't just build a house. You design it to withstand earthquakes, insulate perfectly, and even generate solar power. The implications? Imagine electronics that are not only faster and smaller, but also bendable, like a sheet of paper. Or biomedical sensors so sensitive they could detect diseases at their earliest stages. And energy storage systems that charge in seconds and last for days. The Penn researchers highlight that these materials could also make renewable energy technologies, like solar panels and wind turbines, far more efficient, helping the world shift to cleaner energy faster. But here's the catch. Scaling up this technology is easier said than done. While lab experiments are promising, manufacturing 2D materials at the industrial level requires solving complex engineering problems. Cost, stability, and compatibility with existing infrastructure are just a few hurdles. Some experts argue that traditional materials like silicon will remain dominant for decades, while others believe the 2D revolution is inevitable. Which side are you on? And what trade-offs are you willing to accept for a future powered by atomic-scale materials? And this is the part most people miss. The process of creating these materials is as critical as the materials themselves. The Penn team's insights into chemical reactions and geometric arrangements open the door to custom-designed materials. For instance, by altering the angles at which atoms bond, they can create materials that act as both conductors and insulators, a property that could lead to smarter, more adaptive electronics. But this also raises questions. If we can engineer materials at the atomic level, what ethical boundaries should we set? Could these advancements lead to unintended consequences, like environmental risks from improperly disposed nanomaterials? The debate is just beginning, and we want to hear your thoughts. Do you think the benefits outweigh the risks, or are we rushing into a technological arms race without a clear plan? Share your perspective in the comments below.